And this is part 3 of the solution to this practice SAC, the first practice SAC with the second SAC. We're going to finish the multiple choice section now, continuing with question 10. So once again, we have a combo of 2 questions, 10 and 11. In the energy profile diagram below, I do not know why I start the sentence like that. The activation energy is 243 kilojoules. So activation energy is the energy required to break the bonds in the reactants, and it's always entertaining to watch me try to draw a straight line using this writing pad, which is what I'm doing, and that does not work out too well. But anyway, so the activation energy is 243 kilojoules per mole. Delta H is positive 190, so this is delta H, which is positive 190. And we need to work out the activation energy and delta H for the reverse reaction. So obviously delta H of the reverse reaction is going to be negative 190, and that should cancel out a few options. The activation energy for the reverse reaction is going to be this little segment here, because once again we are assuming that you take the same path going back. So it's just going to be 243, and I knew it was going to do that at one point. 243 minus 190. If I just scroll down a little bit. Okay, so 243 take 190, which, I mean, evidently the answer is 53. And even if you don't know that, the only option left is C, and you can't really have a negative activation energy anyway. Question 11. If a catalyst is applied to the reaction, the EA would, okay, so catalyst will lower the activation energy, which is basically this here. So it's going to lower the EA of both the forward and the back reaction. Okay, so decrease in both the forward and reverse reaction, blah, blah, blah. Answers A. I feel like this is the first A we've got so far. That's totally by chance. Moving on to question 12. And this is our first equilibrium question, I think. So I'm just going to scroll up a little bit so it's a little bit better distributed. All right, I see what I need some. How is that looking? Okay, I think what we're going to do, and well, first of all, I'm not sure why there's a random 2 here. Why is this here? What is it doing? Oh, don't tell me. It's supposed to be up here somewhere. Where would the 2 be? Now that's just odd. Okay, so there's an error with a random 2 that potentially was missing, is now missing from some of the notes up there. Anyhow, question 12. So you have an exothermic system, and by exothermic I mean the forward reaction is exothermic. They always refer to the forward direction when they talk about these things, unless specifically stated otherwise. Come on, why are you doing this to me? Okay, let's try here. There you go. You have K and temperature. A particular reaction mixture contains the following concentrations of gases at equilibrium. So this is already at equilibrium, and you need to work out the temperature of this mixture. So what I'm going to do is I'm going to calculate K. I'm going to call it K2, and I'm going to call that K1. And I'm going to calculate K at this particular temperature, because you don't know whether it's higher, lower, or the same as 460. So you're going to have to compare the 2K to find out. So you have that square over H2 times I2, and all of that should be in concentration. So you will get 0.456 square on 0.0345 multiplied with 0.0835. Okay, and we are going to work out K. All right. I'm just typing on the calculator for anyone interested in wondering what I'm doing. So I got an answer of 72. 0.18. Okay, so this K is higher than the original K of 48.1. And if you have a higher K, that's equivalent to more forward reaction. And the only way to shift the system to the right in this case, because the forward direction is exothermic, if you're shifting to the right, then you must have a temperature lower than 460. So let's just write that down, and the answer is C. And 3 more. Question 13. The gases X, Y, and Z were placed in a sealed container and allowed to reach equilibrium. Okay, I think I'm just going to shrink this tiny bit so we can see the whole question on the screen. Okay, so a gas system. An experiment was conducted with the gases equilibrium at 80. Now forward is XO. I'm not sure whether we're going to need that. Just take a note of that. Concentrations of the gases over time are depicted in the graph below. So something happened at T2 there. It looks like an increase in concentration of everything. So that potentially is going to be an increase in pressure or a decrease in volume by the look of it. Now it doesn't look like anything happened in 3 as far as the concentration is concerned. So we have 4 statements, and you need to find the statements which are consistent with the experimental results. Not the correct statements, the one consistent with the results. In some cases, very rarely, but there are cases when you have a correct statement that just has nothing to do with the situation. It's not the correct answer either. But anyway, let's just read the statements. Successful collisions between gas particles are occurring at T3. Yes, of course, even though you don't see any change in concentrations, you still have successful collisions occurring in both directions. Immediately after T2, the rate of the forward reaction exceeds the rate of the reverse reaction. Okay, so we have at T2 what I think is either an increase in pressure or decrease in volume, and both of which will lead to an increase in concentration, which means that the rate of both the forward reaction and the back reaction will increase. However, because the forward direction has more particles, the rate of the forward reaction is going to increase more as a result of this change compared to the rate of the back reaction. This is something that you need to look at your rate and time graphs and the different situations in that question that we have in class to revise. So yes, 2 is correct too. The change at T2 could be caused by heating the container or by adding an equimolar mixture of X, Y, and Z. Adding the equimolar mixture maybe. Heating the container not, because you have an actual increase in the concentration of the species. So heating, an increase in temperature is not going to do this. The value of equilibrium constant at T1 is different from that at T3. Okay. I don't think so, because it doesn't look like there is actually a change in temperature. There is nothing that you can see here from T3. I mean, it could potentially be addition of a catalyst or something like that, because the concentrations don't change. So I would say that's wrong. So let's hope we have an option that reflects our decisions. 1 and 2 only. It's our second A, hopefully. Okay, so that's 13. Moving on to 14. Now you can tell that, well, this is the first time I'm doing these questions. Just to save time, and I do want to film my working out, but I really don't have that much time to try to do it. I did proofread it briefly before I do this. So let's hope we don't find like a gigantic mistake and then have to refilm everything.